This video will discuss the idea of maximum and minimums and how it applies to calculus. First thing to realize is that in calculus, we refer to two different types of max and min values. Generically, we call all of these extremes, and when we're asked for extremes, we have to realize that does count both max and min. And we've got a couple of quick little ideas and definitions to get through first. The first thing, the idea of an absolute max. The absolute max is the idea that goes along with the biggest y value for a function. So that's what I have here. C would be the location of an absolute max if f of c, the y that goes with c, is bigger than all the other y's for all x's. We'll realize in a few minutes that when we do absolute extremes, we'll almost always have some given interval to go with it, but without that given interval, we would just consider all x's possible. The idea of an absolute minimum would be the exact same, but the opposite. The max is the biggest y value for the entire function. The min would be the lowest y. So we would have f of c is less than or equal to f of x for all x. By the way, that looks like an upside down capital A. That is the math symbol for all. But now to realize those are absolute maximums, the absolute biggest and smallest y value. But next we also have this idea of a local maximum and a local minimum. Other textbooks call them relative max and mins, so I wanted to make sure we're aware of that, but our book normally just focuses on the idea of local max and mins. And quickly, if you just look very quickly, the idea of a local max, it looks like it has the same idea for an absolute max, this idea of a biggest y. But here's the big difference. A local max all has to do with this idea when x is near c. We don't always consider this big for all situation. We always look in these small, tight windows. Is this the biggest or smallest y within a particular window? And that window always must go left and right of a c value that we're considering. So now I have some function here. And just to realize that how we phrase the question makes a very, very big difference. So let's focus on the absolute extremes for a moment. If I just said generically, find the absolute max and min for this function f of x, well, the absolute min would be right here. This xy pair would represent the lowest point on the graph, no matter how far left and right that we look. But if you talk about an absolute max, you might be tempted to point right over here, but to realize the idea is that this keeps going up forever. Not just on one side, but on both sides, we keep going up forever. So is there a point higher than this one? Yes, there is, right here. Is there a point higher than this one? Yes, there is, right here, right here, right here. And that would continue going up forever. So in this full broad sense, there would be no max, and this point would be a minimum. But as I said a moment ago, when we talk about absolute max and mins, we almost always are considering some interval. So all we do, we take that same idea and we apply it to an interval. So if I only want the absolute max min from here to here, well, now I could clearly see this is the highest point and this is the lowest point. And there's your max and there's your min. The end. If I wanted to go from, say, maybe here to here, well, this still is my lowest point. And then I would have a tie. For my highest point, my max would be here or here. If I went from here to here, well, then this would be my minimum. And I think I said about to here, so that this would then be my max value. So I could keep shifting it, and I could go over here. If I go from here to here, then this is my min and this is my max. If I go from here to here, this is my min and this is my max. But notice, in every single one of those examples, if I closed off an interval, we were always able to point out there is a highest y and a smallest y. And that leads us to the extreme value theorem. There is one condition we should have realized. What's nice about this graph up here? The fact that the graph has no breaks or holes, the fact that the graph is continuous. I've got a little bit of a differentiability issue right here at this sharp point, but there are no breaks or holes, so no continuity. no continuity issues, I should say. So the extreme value theorem tells us, and if you read this in the book, all of this, the definitions of absolute and local max and min, the extreme value theorem, the book goes a little bit deeper into the full notation, and it's good for you to read, but I'm trying to make sure in the notes that we get right to the heart of what you need to understand. So the extreme value theorem says, if my function is continuous, doesn't have to be continuous everywhere, but continuous on an interval we care about, then you will always have an absolute max and min. You'll always have extremes on that same interval. And if you think about what we're pointing out as I was going through that up here, every time I changed my interval, I kind of had to refocus on the problem, and there were two possibilities for where the max or min occurred. It occurred either at one of the n values, that would be either A or B in the situation, or it occurred at one of these peak or valleys, depending on exactly our interval. So let's take an extra moment and focus on those peaks and valleys. If I look right here, right here, right here, right here, right here, every single one of those is significant, has that idea of either peak or valley. And what can we say about all of them? Well, let me just change color for a moment. And let's focus on, when we're trying to say what can we say about them, let's focus on the aspect of the derivative. So what can I say about this point, this point, this point, this point? Well, if we think about the derivative, they would all have horizontal tangent lines. That's not a coincidence. There's a big reason why we focus so much on finding where functions have horizontal tangent lines, and we're going to see why that is in just a moment. So those spots, those peaks and valleys, that's a peak. These three are all valleys, but peak or valley, they all have horizontal tangent lines. This is my other peak, and we could talk about the tangent line being vertical, but either way, we've now just figured out the key to the peaks and the valleys. These peaks and valleys all occur at what we formally call critical numbers. Again, our book focuses on critical number. Some other books call it a critical value. But the idea of a critical value is an x-coordinate, so some value c in my domain, such that the derivative at c is 0, meaning we'd have horizontal tangent lines, or the derivative at c does not exist, which is what would happen at this sharp point. Because the last thing, before we start getting some specific problems, this section introduces the general ideas for all max and mins, and we still have a little bit more to say about local max and min, but it really focuses on absolute. That's where most of the problems come up, the idea of finding absolute max and min, and the idea of finding critical numbers. And then in section 3.3, we'll come back and see how we get a better answer for local max and mins. So, back up here and using this function. What can we say about local max and mins? The idea of being the biggest y near c, or for a min, that would be f of c less than or equal to f of x when x is near c. That idea of being near, again, really just focuses on being left and right. So if I just focused right on this point right here, if I cut my graph off right here and only went to the right, I could say that's a high point. But if I go both left and right, well, now I get other points that are higher, as well as others that are lower. So this is not a max or a min. But if you look at a point like this, if you go both left and right, all the points surrounding it are above it, so that this is the lowest point. Now this happens to be the lowest point on the entire function, so let's go to a place like this. This point is actually higher than this point, but this point is a local minimum. Because if I go left and right of this point, all the points that surround it are all above this point. This point would be considered a local maximum, because all the points immediately surrounding it left and right are below this point. So even though this is formally the definition of a local max and a local min, the real idea is that every local max is a peak, and that every local min is a valley. So now I don't care how high or low, and that is one of the biggest things to realize. Absolute max and min are all about biggest y, smallest y, but local max and mins are really about peaks and valleys. That's a peak. That's a local max at this x coordinate. That's a peak. That's a local max at this x coordinate. That's a valley, a minimum at this coordinate. That's a valley, a local min. That's a valley, a local min. I'm not comparing them to each other, just anytime we get a low point like that, whether that's a smooth bottom or a sharp bottom, and same thing with the tops, that's how we identify local max and min values. But again, we'll come back to that later. Let's focus on a function and let's get a little practice dealing with all of this. So the first thing, I gave you a function f of x, and I want you to find the critical values for f. So what we saw, the critical values where the derivative is 0 or undefined. Don't forget about the undefined, everybody. It's easy to get locked in with a lot of problems where we don't have to worry about that, but there are two conditions to consider. So I want to find where f prime of x is 0 or is undefined, does not exist. Well, the first thing I need is the derivative, and this for first example is nothing fancy, nice simple addition subtraction, so I could just do a little power rule and get my derivative. I don't have to worry about the derivative does not exist. We don't have any denominators to worry about here, so I'm only going to worry about where it equals 0, and I'll set it equals 0 to find that, and solve. Remember, very similar. We've done this with horizontal tangent line problems. So I get two answers, x equals 0 and x equals 4. And those are our critical values. But now I want to start asking for absolute extremes, and we're going to do several of these, and I'm just going to keep changing the interval. But it's all about biggest y, but we don't have to check every x. That would be impossible. Even a small interval like -1 to 2, and people mistakenly just check the x's of -1, 0, 1, and 2. They're just checking the whole number values. But realize these could happen at fractions and decimals as well. So what we're going to do to answer all these absolute extreme questions, we're going to make an xy chart. We're going to get the possible x's where the absolute maximum could happen, and those are endpoints, number 1, and number 2, thinking about the critical values, but not all critical values, only critical values that occur in the interval we care about. So we'll list those x's, we'll find the y's that go with them by going back to the original function, and then we'll simply identify biggest y, smallest y to get the absolute extremes. Realize these extremes are xy pairs, so when you give your answer, be sure to label max, min, and have the full xy. So, this first problem, we're looking on the interval -1 to 2. So -1 and 2 go on my list, and any critical numbers, so good thing we already did this. If we did not already find the critical values, that would be something we'd have to do in the middle of this problem. But again, I won't put 0 and 4. I'm only looking from -1 to 2. 0 is in that interval, 4 is not. So these are my candidates. One at a time, plugging them back into the original. So I'll get -1. I get +1 times -6 is -6, plus 7 gives me a y of 0. Now I'm plugging in 2. I get 8 minus 6 times 4, so minus 24, plus 7, and that gives me a y of -9. And then plugging in 0, I get 0 minus 0 plus 7 gives me 7. That is the smallest y value. So this will correspond with my minimum. That is the biggest y value. So that'll correspond with my maximum. But again, we should write that back over here. Don't just leave it on the chart. Put it together. So we get 2 comma minus 9 is my absolute min, and that 0 comma 7 is my absolute max. Same thing for these next two, everybody. Now I'm just going to go right here. Same thing. I'm going to make, again, I know I'm putting these as consecutive problems, but we should really consider this, that it's fresh. I'd get my critical values. I'd list the endpoints given. And now, again, only taking the critical values that fall in that interval. So from 2 to 5, now 4 does fall in that interval, and do the arithmetic. 2 cubed, I get 8. I already did this, right? We just did this up here, so we got minus 9, right? We just did this one moment ago. Notice minus 1 is no longer on my list. Minus 1 is not given as an endpoint. 5 is a new endpoint. I plug that in. Let's see, I get 125 minus 25 times 6 minus 150 plus 7. So we get negative 18. And now when I plug in 4, I'll get 4 cubed, which is 64. See, 16 times 6, I'll get a minus 96 plus 7. And that looks like negative 25. So all negative values, but again, doesn't matter. Biggest y, smallest y. Biggest y is negative 9. There's my max. Smallest y is negative 25. There's my min. And 4, negative 25. Just go backwards for 1 second and realize you change a problem, you change your interval, big things can change. Go back right here a moment ago, 2 negative 9 was the minimum in this problem, but now it becomes the maximum in this problem. Again, it's a new problem. It's just like coming back and looking at a point like this one right here. If I was only going from here to here, that would be a max, but now if I'm going from here to here, now that point would be a minimum. So every time you go to a fresh problem, you have to just consider, treat it like a fresh problem. This previous work outside of the critical values, what we did here didn't help us when we got to here. And now this last one. Now we're checking from minus 1 to 5. So minus 1 and 5. Now notice 2 is not an important x value. I've got my endpoints, and now 0 and 4 both fall in that interval. So now I have 4 x values to check. We don't know how many x's we'll get. We always get 2 endpoints. Maybe there's no critical values. Maybe there's 1, maybe there's 2, maybe there's 3. We have to do each one separately. But once we have all of my candidates, I'm once again getting the y's. We did minus 1 a moment ago. That was 0. We did 5 a moment ago. That was negative 18. We did 0. That was 7. And we did 4. That was negative 25. Biggest y, smallest y. So for our last problem, 0, 7 for our absolute max, and 4, negative 25 for our absolute minimum. Again, just a coincidence. In this problem, both the max and the min occurred at critical values, but up here, only the max was a critical value, the min was an endpoint, the max was an endpoint, the min was a critical value. Again, everyone is separate, just considering get all your x's and then find the y's. So not a bad first problem, and we'll see some more. Absolute maxes are nice. This is what's really going to help us when it comes to word problems, but we'll see for a lot of the calculus that we do, local max and mins will be a little more important for our purposes, and that means just lots more critical values. That's the last thing to realize, everybody. All the local max and mins, all these peaks and valleys, they're all occurring at critical values. So that's going to be a major concern. So finding critical values, where the derivative is 0 or undefined. So taking the derivative, I've got 4 problems here, just going to go one at a time. This first one, again, nice easy function. So my derivative, nothing too fancy. Right, just some nice simple power rule separated by addition, subtraction, setting it equal to 0. I get a little factoring. Can factor some more. And this one ends up with 3 critical values. Go to number 2. Oh, by the way, just backwards 1 second. Simple derivative. Looking at where the derivative is 0, nothing to worry about in the denominator, so nothing to worry about where the denominator doesn't exist, at least not in this one. We'll eventually start to see that coming up a little more often, but never too much, but not to forget where the derivative is 0 or undefined. Now number 2, still need my derivative, This derivative is definitely tougher than the ones we've seen so far. Need some product and chain rule. So maybe do some work on the derivative on the side. I want to focus on the critical value part for right now. So I'm going to do all my product and chain rule as I go along. Derivative of the first, 4 out in front, 2x minus 8 to the third power, inner part stayed intact, times 2, that's the derivative of the inner. All that is u prime times v plus v prime, more chain rule. Derivative of the outer, leaving the inner intact. Technically, we get a times 1. That would be the derivative of the inner, but I'm not going to write the times 1. I want this to be as neat as possible. Times the original u. And believe it or not, go back in your notes. We've seen something like this with horizontal tangent lines. It looks like a big mess, but we've got big terms with common pieces. Big term 1, big term 2. And notice what they have in common. They both have 2x minus 8s, and they both have x plus 3s. So 2x minus 8, and I could take 3 of them out, and x plus 3s, common factors, and I could take 4 of them out. That leaves me, I've got an 8 here, this is out, and I've got an x plus 3 left behind. Over here, the x plus 3s are all out in front, but the 5 is still there. And I have 3 2x minus 8s out in front, but 1 still left behind. These pieces, not bad. Set them each equal to 0. 2x minus 8 equals 0, you'll get 4. X plus 3 equals 0, you'll get negative 3. Don't let the exponents bother you, right? It's just 2x minus 8, 2x minus 8, 2x minus 8. It's the same factor 3 times, so solving it equal to 0 3 times, you're just getting the same answer and over. Same thing here, you've got 4 of these factors, but you only need to solve it once. This one's a little bit messier, just need to do a little more arithmetic. I get an 8x plus 24 here. I get a 10x minus 40, which means I'm really getting an 18x minus 16, right? 8 plus 10x gave me 18x, 24 minus 40 gave me the minus 16. And when I set that equal to 0, add the 16, divide by 18, and you can reduce that to 8/9. Just a coincidence, everybody. We just had 2 critical values on the problem on the previous page. Now this one had 3, and this one also had 3. But that's just a coincidence. We get however many as we get. So a regular one, a little bit harder with a fancier derivative. Now I've got to do it with a trig function. Little chain rule here. C prime of x, 2 cosine x to the first power times negative sign. Then the derivative sign is cosine plus 0. Once again, nothing fancy in the denominator, just setting it equal to 0. Here I can notice I've got a cosine in common. I've got a minus 2 sine x, minus 1 left behind. So cosine equals 0, minus 2 sine, minus 1 equals 0. Add the 1, divide by negative 2. Sine x is minus 1/2. And as we've said, anytime I give you trig equations, I would also give you this restriction. We'll only look one loop around the unit circle. So what angles does cosine equal 0? Well, it equals 0 at 90, which is pi over 2, and at 270, 3 pi over 2. So there's 2 answers. When does sine x equal negative 1/2? Well, sine is negative in the 3rd and 4th quadrants, and sine is 1/2. That occurs at a reference angle of pi over 6, or 30 degrees. So here I'm going pi 180 plus 30, which is 210, or 7 pi over 6 radians, pi plus pi over 6. To here, well, all the way around is 2 pi, but I'm short of 2 pi. I'm short of 360 by 30 degrees, so that means I'm at 330, or 2 pi minus pi over 6 will give you 11 pi over 6. And now we got 4 critical answers for that one. Last problem. Looking at D, Derivative doesn't look that fancy, but just to realize I do need a little bit of a rewrite here. Just bring the x into the numerator. So now I could take a simple derivative, 1 minus 4x to the minus 2 minus 0. And this is where good habits, if we clean this up, it'll be much easier to solve our equation. This is the same thing as 1 minus 4 over x squared. I'm going to get a common denominator here, 1 over 1. So the derivative will end up being x squared minus 4 over x squared. My common denominator was x squared, so I multiplied top and bottom by x squared and put it together as one fraction. And now we finally see the derivative can be undefined because it finally has the denominator. Where does the derivative equal 0? When the top equals 0, and that'll happen at plus or minus 2, factor or solve directly, but we'd also have x is 0. There's one little catch just before we finish this problem. Technically, the idea of a critical value talked about if x was an element in the domain. 0 was already a discontinuity in this problem right in the first place. So technically 0 is not a critical value because it didn't exist in the domain of the original function. So that is true, that is a technical difference. But for all the work that we're going to need when we get to using critical values, we're going to need to include that with the critical values. So it's just a good habit right now. If you don't have a denominator, just setting it equal to 0. If you do have a fraction, set top and bottom equal to 0. There's no better or worse. They're all going to be important x values that we need.